Swayam Prabha. Digital India. Educated India.
Welcome to the lecture 42 of module 9, which is on chemical conversion coatings. In the earlier lecture, we just heard about diffusional processes, so various forms of coatings created by high temperature diffusional processes, whereby we enrich the surface with some specific elements like aluminum, silicon or chromium, which when exposed to high temperature allowed surface protection by way of formation of these respective oxides of alumina, silicon dioxide or chromium oxide. Though there are in situ formation of intermetallic phases, such possibilities exist, but in this particular case, we are going to talk about situations where the surface will react with certain compounds and create in situ certain compound layer, primarily through an fuse bath, reaction with a fuse bath, and form certain reaction products onto the surface which will act as degradation resistant coating or a barrier layer. So, at the first we have to understand that when we are talking about the so-called conversion coatings, what is that we are converting? We are converting the surface into a thin oxide layer or a thin compound layer. Now, if you look at these blackened or dark colored gear components or flanges or connectors and so on, these dark appearance actually appears because of controlled oxidation of the surface. So, chemical conversion coatings basically is a process by which we convert a metal surface from an electrochemically active state to a passive state. So, we would like to convert the surface into a passive state. So, that means from elemental form we want to convert into a compound form, and the compound that we form essentially is a mixed metal oxide. It's not necessarily a pure, it's not going to be pure Fe2O3, but it could be a mixed oxide. And such oxide layer forms on the surface because of this chemical attack. And this is a desired or intentional chemical attack. So, in the process, we actually improve corrosion resistance, we improve the adhesion of subsequent organic coatings or finishes, we improve the wear resistance, we can improve hardness, durability, and so on and so forth. It's a very old and traditional process. It's not one of the most recent ones. So, the typical conversion coatings that we talk about could be based on conversion of titanium or aluminum on the surface into its respective compounds, not necessarily oxides, but maybe mixed oxides or some other compounds, phosphating, then chromating, anodizing, and in such cases we have to enrich the surface. When we talk of chromating, then we actually subject it to a chromium containing solution. Anodizing is a separate process where we actually convert the surface into a certain desired oxide layer, in situ oxidation process. And phosphating essentially means the reaction is with phosphate ion containing bath, so that the surface forms certain phosphide or phosphate compounds. When we look at a metallic surface with an inherent color, immediately we must realize that this color is because of formation of a very thin surface oxide layer, and which is an intentional oxidation. So, depending on the thickness, the defect density onto the surface and chemical nature, of course, we see various appearances of colors. But it is not just coloration alone, it also provides corrosion resistance. So, this thin oxide layer that we form depends upon what kind of medium that we are subjecting to and what temperature and so on. This thin oxide layer also can give us a glossy finish or a bright appearance, and even make the surface quite smooth and even. So when we talk of components made out of iron or copper or brass or any such common metals, and when we subject to such controlled oxidation, either through a alkaline bath or some other chemical bath by way of dipping at room temperature or high temperature, reasonably high temperature, we see a chemical blackening. Now, this blackening essentially is a reflection of formation of oxides on the surface because of the presence of certain oxidizing agent, which could be certain anions on the surface. So, for example, a sodium nitrate or a nitrite solution can be used for such control oxidation. It leads to corrosion resistance, as we already have discussed, improved aesthetics, even can also act as a primer coating for subsequent paint or other layer formation. This also at times gives a dull appearance because of low light reflection or scattering from the surface. And that layer that we are talking about typically will be about 0.75 micrometer or maybe up to about say 0.1 up to about 1 millimeter or 0.1 millimeter or so. The first process of the so-called conversion coating. So essentially we are talking about a situation where we subject the steel component, or for that matter can be copper or aluminum based components also, to a particular solution, for example an aqueous phosphate solution, after of course cleaning the component, making the surface grease free, oil free, so some amount of mechanical polishing or grinding and subsequently chemical cleaning. So the surface is not only cleaned but also is devoid of any contamination. Then and for that one actually also needs certain amount of acid treatment, because the acid will dissolve the other compounds present on the surface. So phosphating is a typical metalworking process adopted in metalworking industry, and to treat substrates like iron, steel, galvanized steel. In fact, it's also used prior to galvanizing routinely, aluminum, copper, magnesium, various other alloys. The principal objective is to improve the corrosion resistance and paint adhesion. So in that case, if it's corrosion resistance, then it's a primary coating. If it's paint adhesion, the intention is to improve the adhesion of the subsequent painting, then this has to be treated as a primer coating. So this kind of metallic component, or even the guns and ammunitions also are routinely, not the entire part, but this appearance is very desired appearance for all those guns and similar ammunition devices. Now, the surface typically will look like this, and if you actually zoom in, then you will see at higher magnification the surface actually is covered by these kind of phosphate compounds. So these compounds are the products of such conversion reactions, and which is what actually offers you the protection. So typically the phosphating bath, which actually allows such conversion coating, will react with the aqueous bath that we are talking about, which will contain certain phosphates and phosphides, and the Me here is the metal, and typically it could be zinc, magnesium, iron, or copper, or some other metals, and they actually this kind of a reaction leads to formation of insoluble metal phosphates onto the substrate surface. The good thing is that since these compounds actually are formed by a reaction between the metallic substrate, a pure metallic substrate, with the chemical solution or the bath, the reaction products are fully adherent onto the surface. So this adherence is one of the most attractive proposition for all such conversion coating. Otherwise, if we coat by some other chemical method, the same compounds, for example, they won't be as adherent as this, because of the fact that these reactions, for example, here that we are seeing, essentially is due to so these phosphate ions are coming from the bath, these anions, and the iron ions, they basically are due to dissolution from the surface. So when they react and then they form either these phosphates or certain oxides, so it's a mixed surface layer, mixed compound surface layer, and the layer, by the by, can either be amorphous, can also be crystalline, depending on the various conditions that we mentioned. But nevertheless, this layer that we form on the surface actually will be will have a good adherence with the underlying substrate. So there is no easy chance of spoliation, and the protection remains for quite some time. So when these kind of compounds form onto the surface, they may be porous, but they are fairly adherent. But when we control them well, so initially when the precipitation occurs, they nucleate in isolated regions, but eventually they'll join and then cover up the entire surface. And if we control well, then the surface contour could be fairly smooth, or in other words, we can actually reduce the amount of porosity in it. But again, I would repeat, the main attractive proposition here, or the reason why this is a very desired process, is because of the high amount of adhesion of the compound layer that forms. Very routinely used in automobile industry. In fact, almost all the bodies, the automobile bodies, actually undergo phosphating as a primary process before the paint is applied, or the doors, panels, bonnets, and all other metallic parts are painted. So one goes through degreasing, rinsing, then phosphating, and again rinsing, then the coating process of the paint that we do. Then we drain the excess paint, and then we bake so that the paint actually polymerizes and becomes adherent to the surface. And then we also apply certain epoxy or some other polymeric coating to seal the porosities or gaps onto the surface and make the surface appear absolutely smooth, flat, and glossy. So before actually this paint is applied by way of dip coating in a controlled manner, of course, it is important that the surface of the metals of the automobile bodies are actually subjected to phosphating. And this phosphating acts as a primer on which such paints are applied, and the paint actually now enjoys a better adherence and stability on the metallic surface. So a steel surface, a steel sheet, for example, directly given to this kind of a paint or coating will not be as adherent as the case when you go through the intermediate process of phosphating as a primer coating and then subjecting to the painting. So this is the steps, as we all saw, cleaning followed by rinsing. This cleaning could be purely in aqueous bath, or could be even acid cleaning. Then if it's some acid or alkali cleaning, then you have to rinse and remove the remnant acid or alkali. And that's when, after rinsing, the surface becomes fairly active. Then we subject to phosphating process. Again, we remove the remnant residual phosphate ions from the surface, because we don't want the oxidation to continue forever. So the residual phosphate ions are removed by rinsing. Then we also do a neutralizing rinse, which essentially means that if there is some pH control required, that is done at this rinsing stage. Then we dry it out so that there is no residual ions remaining. Then we do the supplementary coating, which is the painting process. And then if required, we do some baking and then drying, and then the surface is ready for use. So we want to improve the corrosion resistance. We can, if we are coating with zinc or manganese, then the galling wear process is or the chances of galling is reduced. It improves the adhesion for paint overlayer, which is to be applied subsequently. It can provide electrical insulation and barrier. The porosity and other things can be actually interlocked during the drying process. And zinc phosphate coating is very routinely used in conjunction with sodium stearate to form lubricating layer on cold and hot forging dies. Just a comparison, as I said, that depending on the defect density and the process parameters and the conditions, the phosphate layer that we form can either be amorphous or crystalline. In fact, if it's crystalline, then of course the coating thickness and the amount that we deposit is higher. But in case of amorphous layer, we have more porosities and defects. So as a result, it is applicable to low painted or unpainted corrosion resistance, and it gives a poor unpainted and low painted corrosion resistance when we are talking about amorphous layer. But in case of crystalline layer, which is slightly thicker, actually, though it is slightly expensive, but the corrosion resistance will be much higher compared to the amorphous layer. So instead of phosphating, we actually can think of another conversion coating, which is chromate based. So the active ion, the anion which actually reacts in the bath now is chromate ion. So we use this again is very useful for substrates to passivate components made out of steel, aluminum, zinc, cadmium, copper, silver, titanium, and a host of various metals. So here again we have to immerse because we have an aqueous bath or a fluid bath, and then we allow the component to stay for a while. So you dip the part, and then so you dip in chromic acid and then dip for a while. There could be agitation or circulation, or in still bath, and then you withdraw. So this is when you charge, this is where you allow certain circulation, and this is where you withdraw, and then you dip inside water or some other fluid layer so that you can remove the excess chromium on it, and that needs to be removed. Removal of the residual chromium ion is very important because here we are not talking about tetravalent, but we are talking about a hexavalent chromium layer. So obviously hexavalent chromium layer is or hexavalent chromium is has certain high level of toxicity, so this needs to be removed very clearly, completely. So the coating that we generate usually is soft and gelatinous, but generally it hardens and becomes hydrophobic after a certain period of time. So this is basically the curing period, and this curing can be done at room temperature or at slightly elevated temperature. But if it is for either higher temperature than usual or longer time at the given temperature, it may damage the coating on the steel. In other words, it can lead to unnecessary progress of reactions, and the reaction products could be fairly brittle. And in fact, after the chromating reaction, the surface layer actually can form such rivulets of cracks or interconnected cracks. So these regions they form because when these compounds form, there could be changes in the specific volume, and as a result, there could be crack forming all over the surface. So there could be cathodic reactions, there could be anodic reaction, and these reaction products basically provide the, for example, these are the protective oxides. So either chromium hydroxide or zinc hydroxide, depending on what kind of reaction products we want. So we want corrosion protection, corrosion inhibition. We can use as a primer coating, just like phosphating, decorative finish, as electrical insulation layer, or on hardware tools also, typically for aesthetics and all. So when we are using chrome plating, usually the surface is bright. In fact, it can be also shining, silky shining type. When we use chromate with zinc, then we get clear coating, but it may also give us some yellow or black tinge depending upon the relative concentration of this and the amount of oxidation that takes place during the coating itself. We can also use chromate coating without zinc. There we get a yellowish tinge, or it can be for a thicker layer, it can be black, and this blackness comes primarily because of the thickness of the coating and also roughness of the coating or porous nature of the coating, which leads to a lot of scattering of light. We can also use various other additional coating processes. So typical applications could be in transmission parts, mandrels, gears, extrusions, extrusion dies, tools, fasteners, hinges, electronic components, waveguides, and also as a pre-treatment prior to coating larger surface, so as a primer coating. So this is how typically an aluminum chromate conversion coating looks like. Another process which also requires chemical reaction, which also undergoes reaction. So in case of phosphating, we used a phosphate containing bath, aqueous bath, which reacts with the cation, the metal surface, and forms certain oxides and phosphates and mixed compounds. And that can actually give the protection. That can also be used as a primer coating for further addition of paints on it. The same thing happens in case of chromating, where we use chromate containing bath or chromium containing bath, typically hexavalent chromium containing bath. So we use chromic oxide based bath in which we dip and then we allow the surface reaction to occur. In case of anodizing, we have a slightly different and a more interesting process. Here we actually, first of all, let me mention that the intention is very similar: decorative, durable, corrosion resistant, anodic oxide finish, and usually applied to aluminum, because aluminum actually is a material which is very widely used as the anode in any anode in an electrolytic bath. And when it is used as an anode, it has a tendency of formation of aluminum oxide on the surface, because as we all know, typically in an electro deposition bath, the anode gets dissolved and deposits onto the cathode. So the cations move out of anode and go and deposit onto the cathode. But the anions, when they are dissolved, if there is a certain concentration of anions present in the vicinity, then the released cations can actually react with the incoming anions and form an oxide or a compound layer. And that's exactly what's happening here. So we first clean in a typical caustic soda bath and make it absolutely clean. And then we take it to an electrolytic bath, typically where we actually have the two electrodes, the anode, the positively charged, and cathode, which is, for example, here is a lead cathode, negatively charged. So we expect, if this is aluminum, we expect aluminum to get dissolved, but before actually it goes and can deposit onto the cathode, it can react with the anions present in the bath, typically the oxide ions, and then form a thin oxide layer around. And these alumina or aluminum oxide actually can be useful for coloring or sealing, and also as a protective layer. So it is both ordered at the same time porous structure. So we need an acid electrolyte bath, because otherwise there will be no ionic dissociation or electrolytic conduction, where ions will move from one end to the other. In the process, there will be an electric current created, and since aluminum is acting as the anode, aluminum suffers oxidation and converts part of its surface up to a certain depth into its oxide. The pertinent question here is that we spend so much time and energy and money or cost to convert aluminum oxide to aluminium, and in anodizing process, we again are converting the surface into its oxide. So going the reverse direction, then why did we spend so much money to win aluminium from alumina? If we wanted to create alumina out of aluminium, the answer is very simple, that when we create this alumina layer, it is only a very thin layer onto the surface, but fairly adherent. And in the process, this Al2O3 layer on Al, aluminium, can protect aluminium from further degradation during use. So essentially, we are the process of degradation means it will convert the cation into its oxide or metal into its oxide. We are doing that beforehand so that no further such degradation happens during the applications, during the use. So the process involves typically cleaning, just like any other conversion coating, cleaning, pretreatment, brightening, and then etching, and then comes the anodizing process. That means then we subject to such an electrolytic bath where we apply current from outside through the battery. So this is a driven process, and from the anode the cations get dissolved, and so these are the cations that get dissolved. The anions come and attack the anode, and the cations then react and then form a thin aluminum oxide layer on surrounding the anode, which is aluminium in this case. Applications could be for architectural parts, aesthetic reason, food processing equipment, power cylinder, fluid power cylinders and parts, pistons, nozzles, pumps and valves, gears, brakes, hinges, swivel joints, keys, aircraft wheels, automotive trims, picture frames, molds. So these are both for aesthetic purpose, architectural purpose, as well as for structural applications, load-bearing applications, like brakes and hinges and gears and so on, pumps and valves. So it's a very thin layer that we convert to oxide, and mind you that we are talking about aluminium as the substrate and no other metal. So in the process, when we subject this aluminium to such anodizing process, conversion of oxide form, this is a research publication which shows how such anodizing improves resistance against or attack of tartaric sulfuric acid. So in fact, in the presence of cerium, and the cerium nanoparticles actually help in providing protection. And as we can see that in untreated condition, we have larger dissolution, faster rate of dissolution compared to the case where we have cerium particles, cerium nanoparticles present in the bath, and they form a coating onto the surface alongside anodizing or surface oxidation. So that gives us more protection. So we'll stop here, but before that we have to ask ourselves that what is the principle of conversion coating? What are we converting? Then is it always a primer coating or a base coating or a final coating? Both are possible. This is what we were discussing, as that we spend so much time and effort to win aluminium from its oxide ore. Then again, why do we convert the surface? But we are converting only the surface up to a thin layer so that the base component made out of aluminium is protected. Then in all the processes of conversion coating, surface oxidation is the key to convert the metallic surface up to a certain depth into a compound form which is stable and corrosion resistant. So the corrosion resistance and ability to improve the surface adhesion of the subsequent layer, these are two reasons why conversion coating is so important. Chromizing or chromating or anodizing, there are certain differences. Say for example, when I say chromating, we are talking about conversion, reaction, but chromizing, what we discussed earlier, is a diffusional process where chromium does not react immediately, remains as solid solution. Similarly, anodizing is different because anodizing is not typical calorizing process or aluminum diffusional coating process. In anodizing, we are converting aluminum into corresponding oxide by way of surface oxidation. We need to know what is anodizing mechanism, what are the precautions to be taken to maintain the bath activity, and also when do we choose chromating, when do we choose phosphating before galvanizing, and whether the oxide conversion coatings and anodizing, are they the one and the same? The answer is no, because here we see a reaction, a chemical reaction between the metal substrate, its surface, and an aqueous bath containing certain aggressive ions, whereas anodizing is an in situ oxidation of the aluminum substrate itself. So we'll stop here. Thank you very much.